Alright, 4.4 derivatives. I know, but you didn't know that's what we were still doing. Exponential.
Oh, that's all. Sorry.
And logarithmic functions. Also, I have stuff graded for y'all that I don't think I gave back yet. So.
No, I didn't want it back.
It wasn't the time nor the place.
So I need to give that back to you at the end of class, but. Alright, so first and foremost, we're going to have the derivative of e to the x.
Is this more memorizing?
Yep.
Okay, I can do that.
This one is the easiest one. But I'm going to drive it for you anyways.
Okay.
d dx of e to the x. Like, if you forget this one, it might actually make me sad.
I won't forget.
Is the limit as h approaches 0 of e to the x plus h minus e to the x all over h. So then I have the limit as h approaches 0 of e to the x, e to the h, because remember when we multiply, that's when we add the exponent, so I can split it, minus e to the x divided by h. Now, because I have an e to the x in both pieces, I can take it out. So that would give me the limit as h approaches 0 of e to the x times e to the h minus 1 over h. Now, because of this being basically like a constant, because it's just a number raised to a power, I can take it out front. So I have e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now, from back in like chapter 1, it told us that this was equal to 1. So this ends up being equal to e to the x times 1. So, come back. The derivative of e to the x is e to the x.
Oh.
I can see
Okay.
why you'd be sad if
I'd be very sad if
My prediction was correct.
I'd be sad at myself.
Now, that's obviously in the most basic form. If it's a chain rule, because x, say, is a function, then obviously it's a little harder than that, but it's still the same thing, basically. So yes, don't forget that. Easy derivative. Now, the chain rule for this is d dx of e to the u, where u is a function, is e to the u du dx. So it still gets copied down, and then we just take the derivative of whatever the power is the only difference for that one. So notice this is e to the x, where e is the number e. Okay, this isn't just like a random constant and something specific. Because I also have the derivative of a to the x. So if a is greater than 0 and a is not equal to 1, use the property of logs to write a to the x in terms of e to the x. So a to the x is equal to e to the x ln of a. which gives us then e to the x ln of a is equal to e to the ln of a to the x times the ln of a which ultimately gives us a to the x ln of a. So the derivative d dx of a to the x is a to the x ln of a. And a is, again, just a number. So that's the derivative of a to the x. It's a to the x ln of a. We obviously would have a chain rule for this as well. And all the same stuff applies. A greater than 0, a not equal to 1. So d dx of a to the u is a to the u, so whatever that value is, we write it down, times the ln of a, so whatever a is, same thing, times whatever the function u is, so times du dx. All right, so those are the derivatives of exponentials. Now we're going to move into the derivatives of logs. So the derivative of ln of x we've got y equals the ln of x. So if I raise both things like e to all of that, so basically e to the y is equal to x, or I like basically take the inverse. This is the inverse relationship. It's also the same thing as taking both things and raise like e to whatever that is, which we can do by property of logs. Anyways, but it gives us that. Differentiate implicitly, so that would give us e to the y prime is equal to 1. So y prime is equal to 1 over e to the y. We said e to the y was equal to x, so this is 1 over x. So d dx of the ln of x is 1 over x. So again, super easy. Fortunately, these aren't like crazy like the inverse trig ones. They're a lot easier to memorize. And as I'm sure you can guess, we have a chain rule for this as well. d dx of the ln of u 1 over u du dx. Now, that's of the derivative of the natural log. A derivative of a log base a of x is next. So log base a of x is equal to, this is the change of base formula, the ln of x over the ln of a. So if you forgot the change of base formula, that's what it is. Peyton may remember it because that's how she had to put everything in her calculator last year.
I'm definitely glad I got the calculator. This was stressful.
So when I'm taking the derivative, I'm going to use this as the change of base just because it makes things easier in terms of finding or deriving the derivative. Once we get it, you'll actually have a formula that you'll use. So d dx of log base a of x is d dx of the ln of x over the ln of a. Now, would you agree that 1 over the ln of a is a constant value? Yes, because a is a number. Okay, so what I'm going to do is I'm going to make this 1 over the ln of a times d dx of the ln of x. And that's because ln of a is constant. And we already know what the derivative of the ln of x is. It was
1 over x.
1 over x. So this is equal to 1 over the ln of a times 1 over x. So ultimately, d dx of the log base a of x is equal to 1 over x times the ln of a. Chain rule. D dx of log base a of u is 1 over u ln of a times du dx. All right, and then the last thing is a power rule, which we've already kind of seen. It's just going to be written a little differently for arbitrary real powers. So if x is greater than 0, write the real power of x as a power of e. So x to the n is equal to e to the n ln of x. So d dx is going to be e to the n ln of x times the derivative of this stuff at the top, because remember we copy it down once, then we take the derivative of all of that, so the derivative of n ln of x, which is going to be e to the n ln of x times the derivative of this is just going to be n over x, because derivative of ln of x is 1 over x, and n is just some number. E to the ln of x we said was equal to x to the n. So this is x to the n times n over x. And so this just ends up being n, x to the n minus 1. And so simply was just another way, or maybe not so simply, to write the power rule that we've already had a million times. So that's the notes. I think we're going to be ready for some examples.